So I've been doing this a really long time, and today I'm hopefully going to share with you a little bit about what I know in one of my favorite topics, and that is, how it is that systems interact between different types of signals. So, we talk about a particular system, an electronic system. There's a number of different disciplines, and some of these you're probably familiar with. There's power electronics, which is what Andy was just talking about. And that's pretty much the design of, of the VRM, or the silver box power supply. And that's where we do the front end conversion of some intermediate bus or AC input mains, and we convert that to raw DC output. There's power integrity, and that's a little bit different, but that is really the transfer of power and the distribution of power between the voltage regulator module and the rest of the system. And the goal for power integrity, of course, is to make sure that each of the devices in the system gets power that it can tolerate or even thrive with. And then, of course, we have signal integrity, and that is our data channels. And much of our systems are based on data channel transmissions and communications. And so a lot of our systems are designed around achieving signal integrity. And then there's also EMI, and all of our systems are sensitive to EMI, not only from a susceptibility standpoint, but also from an emission standpoint. And a lot of conferences now tie some of these together, and I think the most popular trifecta is SI, PI, and EMI. And there are a lot of conferences and also magazines now that tailor their content to these three topics. Of course, leaving out power electronics is a really big issue, and that's one of the things we're going to talk about today. And there's also other disciplines. There's RF and microwave, right? So in your cell phone, you have Bluetooth and you have Wi-Fi and near field. There's millimeter wave stuff. That's the new 112 gigabits and 5G. IoT, there's a lot of analog and low-level sensors. And of course, there are other disciplines like thermal design and structural reliability. But today I'm going to focus on the four on the left-hand side: PE, PI, SI, and EMI. And even more importantly, how it is that they interact. So when we talk about power electronics is really focused on the performance of just the power supply. That's the point of load switching regulator, linear regulator, multi-phase VRM, but it's that main power conversion. And the power electronics engineer has specific figures of merit, and I provided a list here. It's not a complete list, but a partial list. So we're interested in efficiency, and that does tend to be one of the most important these days. Size and weight, we do want them to be really small, and you'll notice that Andy was talking about his 16th brick, so they're getting smaller all the time. EMI is a big issue that PE engineers are concerned with. Output impedance, and that's a really big one. Andy touched on impedance, but impedance probably is one of the most important criteria in the system, and one that I'm going to be focusing on today. Of course, there's DC regulation, and there's transient response that Andy also mentioned, and there's voltage ripple, and there's also cost. And these power electronics systems come in all different flavors. So there are multi-phase VRMs, and these can get quite large and many phases. I think the largest ASIC I've seen to date is 1,600 amps in a 100 millimeter socket, and so these power supplies can be quite large. On the other end of the spectrum, we have high-density electronics, cell phones, and things like that, and those generally concentrate power supplies into power management ICs or PMICs, and there we can end up with anywhere between maybe a dozen and I think the largest I've seen is about 80 power supplies inside a single chip, and all of these comprise power electronics. Power integrity, like I said, that focuses on the interconnect between the VRM and the rest of the system, and it distributes and routes power through power planes and And it includes the decoupling capacitors and filtering and whatever else it is that we need in order to assure power quality at the high performance ASICs. And so there is this interface between the VRM and the rest of the system that we have to be consciously aware of, where there's this handoff between power electronics and power integrity. And often this is defined by specific characteristics, and one of the most important is target impedance. And target impedance tells us the impedance limits that we need to match at the ASIC in order to meet the demands from high-speed system power. There's also ripple and noise and excess inductance as we get to the ASIC, and these are probably the most important characteristics. One of the things that's really underplayed in power integrity is that there is significant interaction between the voltage regulator module and the rest of the system. And while target impedance is focused on the transient response, where the transient is generated by the high-speed ASICs, there are lots of other noise paths from the power supply that also get into the system and need to be considered for power integrity. Signal integrity actually takes the data streams and it transmits them across the circuit boards and gets them to receivers. So we have transmitters on one side and receivers on the other, or more commonly these days, transceivers on one end and transceivers on the other end. Engineers today are pretty familiar with the fact that jitter is dependent on power supply noise, and in fact, the single largest source of jitter is the power supply. And so a lot of simulation today is done with power-aware IBIS models. IBIS model is kind of a standard that allows engineers to share data about the rise and fall times and parasitics of their high-speed devices without sharing what they would consider to be intellectual property. So IBIS is kind of a portable model that hides all of the details that companies don't want to share, but providing sufficient information in order to allow engineers to simulate it with it. And most IBIS models today are power aware, and they allow us to do noise interactions in real-time simulation. Andy stole pictures from me, so I'll fess up that I stole these images from Heidi Barnes at Keysight, and she talks an awful lot about power issues in SI channels. And then there's electromagnetic interference, or EMI, and this is really a focus of conducted and radiated signals that escape from electronic circuitry. If you've taken my online classes, you'll see that this is really also a bidirectional thing. So on the one hand, we all worried about high frequency noise escaping our electronics into the air where it can interfere with other things. We're also susceptible to noise getting into our systems in exactly the same way, and in fact, using the same antennas. So EMI engineers are, focused on making sure that we don't have unbroken return paths, that we have tightly sealed enclosures, that we minimize coupling between, power leads and signal leads. And of course, they want to try to make sure that we don't have any IQ impedance peaks. And you can see here we have this nice sharp impedance peak, and that correlates with noise. And you can see that transient noise in the time domain in the lower trace. And so that's the focus of the EMI engineer. Unfortunately, these really are not independent functions. They all interact with each other. And while the engineers may not, that's probably the source of most system issues today, is that we can make the perfect power supply, but its performance is going to change as soon as we attach it to a system. And we, remove our local sense, and we use remote sensing lines throughout the system, and those remote sense lines also impact the performance of the power supply. And so SI, PI, PE, and EMI all interact with each other. And so if you look at this Venn diagram, you can see all of the different effects that come from one to the other and where it is that they overlap. And so this is kind of where my interests lie these days, and the majority of my focus is on the holistic design of systems. And the holistic design means that we can't really design a power supply without understanding what it is that it's connected to and how it is that we're going to impact the system and how the system is going to impact us. But there is actually a common thread that ties all of these together. And you may have noticed that in each one of these slides, every time I mentioned impedance, I colored it in red because that is the common denominator. All of the performance from power electronics, power integrity, signal integrity, and EMI can be measured and qualified and quantified by the measurement of impedance. And so that's kind of a key interest. Now, there are some popular beliefs, and most of them aren't true, but one is that interactions are limited to high frequency or high power, and that's absolutely untrue, as I'm going to show you soon. And of course, impedance isn't the only issue, but let's try to take a look at a few examples to see how it is that this works in a system and how it is that noise transfers among the different disciplines. So one is PE and how that relates to SI. And again, I'll fess up to stealing this slide from Bruce here in the bottom. And I've actually emailed with Bruce a little bit because I love this slide and I show it a lot. The interesting thing about this slide is I'm showing the oscillator schematic in the white portion of the schematic. And you can see it's relatively simplistic with a couple of transistors, a crystal, some ferrite beads, and a transformer to couple power to the output. So it's not really very sophisticated. It's pretty simple oscillator. And this oscillator is specified to be ultra low phase noise, meaning that it doesn't really have jitter. But the reason I like this slide and the thing that I wanted to focus on is that the power supply is the part that's in pink. And so while this is an ultra low phase noise power supply, ultra low phase noise oscillator, the majority of the circuitry is power supply. And that's because that's where most of the phase noise and jitter come from. Master oscillator designer Charles Wenzel knew this. He knew it really well. And he spent a good part of his career looking for ways to reduce power supply noise for the performance of his ultra low phase noise oscillators. In this case, you can see there are active bias circuits using transistors. There's something referred to generally as a Wenzel ripple stripper in the upper left-hand corner. That's a transistor configured as a capacitance multiplier. And it essentially makes the input filter capacitor look nearly infinite. And that takes most of the ripple off the input lines and strips it before it gets to the oscillator. On the right-hand side, you can see that there are multiple voltage references. In fact, there's 4 LM129 voltage references in an active current loop. And those are used to average out the noise. Honestly, it's not very efficient. It's the square root of the number of devices. So using 4 devices, we can reduce the noise in the bias loop by about 6 dB. But for the purposes of what I wanted to show here, it just shows that the power supply itself is the major source of the SI noise that comes from the reference clock. And of course, once power gets into the reference clock, the jitter is everywhere. We can address this in power-aware SI simulation also, and I showed this in my series, Designing Power for Sensitive Circuits. And here's a relatively simple low phase noise oscillator schematic on the left, and this is just a simple simulation in Keysight's ADS using harmonic balance phase noise simulation. And you can see in that schematic, I'm also able to add noise to the power supply. And in this case, you can see I added power supply as a noise density being about 250 nanovolts per root hertz. And you can see that the phase noise floor raises from the red trace to the green trace. So we actually increased our phase noise floor by about 15 dB just by adding 250 nanovolts per root hertz to the power supply. And of course, we can also design a filter, and you can see that R filter and C filter in our schematic on the left. And if we size that filter exactly right, you can see we can get the phase noise right back to where it was. And while we don't want to under-design and we don't want to over-design, there is an exact solution for that filter. And if you're interested in that, I talk about that a lot in designing power for sensitive circuits, and I show you exactly how to design the precise filter that's not over-designed or under-designed. But here are a few slides from that designing power for sensitive circuits presentation. One thing I wanted to show is what the switching regulator switch node looks like, and that's on the left-hand side. Again, just before this presentation, Andy Ryder talked about, how jitter comes about in the intercurrent loop. Power supplies do inherently have switching frequency jitter, and it comes from a number of sources. One source is spread spectrum. So a lot of VRMs today actually do modulate the switching frequency in order to minimize EMI. But also the oscillators in most switching power supplies aren't very sophisticated. And because they're not very sophisticated, we can see jitter there also. One common mistake that engineers make when they look at these signals is they tend to trigger the oscilloscope, and then they look near the trigger. That would be the bottom trace. And that doesn't look so bad. There's maybe just a little bit of jitter on the trailing edge, but it's a pretty clean signal. If we just delay the data and we look at that same trace 62 microseconds later, you'll see the upper trace. And there's a couple of things that are notable about that upper trace. One is that both edges now are modulated. And that tells us that we see both duty cycle modulation and also switching frequency modulation. Both of those turn out as jitter, and that jitter turns out to be voltage ripple. That voltage ripple can be very small. The slide on the right, this image also is from designing power for sensitive circuits, and this happens to be the oscillator on our VRTS3 demo board. And that VRTS3 demo board allows us to power that oscillator from two different power supplies. One is from a low dropout, low noise linear regulator, and the other one is from a switching regulator. And we can look at the phase noise of the clock using both of those. And you can see that the phase noise is the worst from the switching regulator. That's the green trace. And actually at about 2.8 megahertz, you can see that peak, and that peak is the switching frequency. And so you might have expected that the switching regulator would have the most jitter, but the interesting question is the jitter is about 25 kilohertz. Why would it be at 25 kilohertz when the switching frequency is 2.8 megahertz? And the answer is because of that modulation. That modulation creates almost a millivolt of noise, and that millivolt of power supply noise causes that green trace. And if we look at the linear regulator, well, you can see that the noise is lower. And in fact, in the bottom right of that same plot, you can see the jitter. So the jitter of the switching power supply is 22 picoseconds. And going to the linear regulator reduces that by a factor of almost 3, maybe a little more than 3, to 6.6 picoseconds. But you'll notice the peak is also at about 30 kilohertz. And finally, we can power this from an external power supply. So we got as close to noise as we could. We used our J2120 line injector, which has about 2 nanovolts per root hertz of noise, and you get the blue trace. And you can see the phase noise gets all the way down to 1.5 picoseconds now, but still has a peak at about 20 kilohertz. Why is that peak always at 20 kilohertz? The reason is because that is the phase lock loop bandwidth inside the reference clock. And that phase lock loop has a somewhat unstable control loop at about 25 kilohertz or so. And so independent of the power supply, we see a peak there. And the more noise we put into the power supply, the more jitter we get. Now, of course, power electronics engineers are really interested in things like efficiency, right? And so one of the things that many power electronic circuits include today is burst mode, chirp mode, or PFM mode. And these are modes that go into chirp or burst or cycle skipping when we get to low power in order to improve efficiency. And what I wanted to show is what that looks like when you measure it as phase noise in the clock. And here we went from about 40 picoseconds in a normally operating power supply. You can see both traces there on the left. The bright yellow one is when the power supply is operating normally, and we get 40 picoseconds of jitter. And we go into this burst mode to improve our efficiency. The jitter increases to about 700 picoseconds. So about 18 times the jitter, 18 times the phase noise. And so while the power supply guy might really be proud of himself for improving the efficiency, of course, he impacted everybody else by destroying the signal integrity through the reference clocks. And this is really what I'm trying to get across, is that this is a holistic system. We're not really operating independently. And power rail resonances also result in SI. So this also is the impedance of the power supply in one operating condition, where we can show an unstable VRM, and we see the peak in impedance on the left at around 50 kilohertz or so. We can also see a power plane resonance up around 7 megahertz. And again, as Andy noted, when you see these peaks, they're going to result in noise. They're going to be noisy just based on noise density from the system and also from excitations. And this impedance tells us a lot about what's going to happen in the systems that it's connected to. And so I set up this same board again, and here I'm looking at what that looks like if I were to put a load perturbation on the power supply that the clock is connected to. And so in the top trace, I'm looking at the 125 megahertz reference clock. In the middle trace, I'm looking at the current waveform. So I'm just putting in about a 20 milliamp step into the 3-volt power supply. The bottom trace is showing me the frequency of that reference clock. And you can see that the frequency bounces in response to this transient. And because that resonant is high Q, you can see the ringing that shows up in the frequency as it settles out. And of course, during this transition, we have poor signal integrity because the clock oscillator is jittering. And if you could look at the distance between these peaks, we could measure the frequency of that ringing, and it would be around 7 megahertz, which is the high frequency peak in our board. Now, of course, most systems don't just have one power supply, they have many. And so what does that look like when a power supply turns on and off? Well, every buck or step-down regulator turns on a switch to connect the input to the output, and then it averages that by controlling duty cycle over time. See, here I have a 1 megahertz switching power supply, and it's operating at about a 20% duty cycle. And so we can actually see the power rail noise that's related to that switch. Every time we turn on the switch, the output current flows through the input. We put this large current step into the voltage regulator input, and that gets into the power line bus, where it goes through just about everything. And again, if we look at our reference clock, you can see that our 125 megahertz clock falls as low as about 123 megahertz and up about as high as about 127 megahertz. And so again, we've impacted SI just because the power supply switch is turned on. And if we were to look at the spectrum of that oscillator, you could see this 1 megahertz from the switching regulator that shows up in the spectrum, and all of its sum and difference mixing frequencies. So there's a lot of spectral content there that occurs because of it. Now, I showed that there were 2 different resonances in that power plane on our VRTS3 board, one at 7 megahertz and one at a lower frequency. And if we could generate an appropriate load step, we could excite both of those. We could excite both of those simultaneously. And if we put those bursts in just the right position, we can create rogue waves. A rogue wave is where we take transients that each have independent functions, and we phase them such that we can stack their responses one on top of the other. And that'll give us a much larger transient than any individual response could. And here you can see we have these rogue waves that show up in response to a burst. And where do these bursts come from? Well, that is the data from our ASIC. Now, of course, we are interested in EMI also. So here was a challenge. There's an encapsulated Vicor module underneath that heatsink. And the question is, could it determine the turns ratio of the power transformer without probing the module, opening it, or x-raying it? Turns out that that's a pretty simple thing to do, and it only took me a few minutes. But just putting an antenna next to the module, and you can see on this picture on the left, I have a near-field probe, and I just placed it right next to the module. If I look at that on an oscilloscope, well, you can see I have a pretty nice picture of the switching waveform. In fact, as I change the load, I can see the duty cycle change. I can see a lot of things about the power supply from this picture. One thing you might notice is that the quasi-resonant edge, so you can see the near zero switching here in the resonant edge in order to improve efficiency. But we can also see where the switch is on, and we can see where the switch is off. We can even see the ringing in the transformer. And then, of course, we can see the plateau. This is where the power is delivered. So we were able to determine quickly that this is actually a flyback power supply. Now, we do know that during the time that the switch is on, we apply the input voltage across the transformer. And then while the switch is off, we apply the flyback voltage across the transformer. And after it's become depleted, well, it just zeroes out at the null point. And so here we can see, here's the 48 volts from our input power supply. And we can see here's the flyback voltage. So the ratio of those two allows us to determine what the flyback voltage is. And that allows us to tell that the turns ratio of the transformer is 2. So that was pretty easy. Of course, I can tell a lot more about it. I can see the frequency, I can see the on time, and I know the output power. And so I can solve the equation for power related to switching frequency, on time, input voltage, and primary inductance. So I can also tell you what the primary inductance of that transformer is. And in this case, it happens to be about 2.5 microhenries. So we can tell an awful lot from that EMI. And it's one of the reasons that we don't want EMI. In fact, back in the 1950s, it was observed that EMI from large systems, things like submarines and airplanes were relatively big ones. Return signals often carried through the skins of the submarine and the aircraft. One of the things that we learned in the 1950s is that spies were able to intercept our data by looking at the EMI from the skins of the aircraft and the submarines. And so they came out with a new requirement called TEMPEST, Telecommunications Electronics Materials Protected from Emanating Spurious Transmissions. That's a really big word, so that's why they call it TEMPEST. The whole idea of TEMPEST was to make sure that there are no currents in the skins of submarines and airplanes, because those are large antennas, and it allowed us to interrupt signals. We could actually get the data streams directly from the skins. What does a simplified step-down regulator look like? It looks quite simple, really. It's a half bridge, usually. So we have an input capacitor, and then we have a top switch and a bottom switch. And then we have an output inductor and an output capacitor. And of course, we switch these two MOSFETs on and off at the switching frequency and at some duty cycle. And then the output filter averages that to control the output voltage of our regulator. But one of the things that we see from that, and one of the common misunderstandings, I think, is that that generates noise, and it generates an awful lot of noise, and that noise is independent of power level, and it's also independent of switching frequency. And I show that using this simple CMOS logic gate on our VRTS3 board. This little logic gate is connected to the oscillators, and so it's switching on and off at some rate, depending on which clock it's connected to. There isn't any loading on it. It's just a logic converter, and it just goes high and low. And in this case, I think this is a 10 megahertz clock. And you can see that when it switches on and it switches off, if we look at the power supply, we can generate tremendous amounts of noise. And in fact, in this case, you can see for our nominal power supply voltage is about 4.4 volts, and it falls as low as about 3.6 and goes up as high as about 5. So we have almost 1.5 volts of noise coming from a logic converter that's not connected to anything at the output. There is no loading on it. It has a series resistor and capacitor for DC blocking, but there is no loading. So we're just switching the logic gate. Where does all of this noise come from? How can it generate so much noise when the average current into this logic gate is 0, or very close to 0? Well, it kind of looks like this. Looks a lot like a step-down regulator. There's a half bridge inside that logic gate. And of course, every connection we have has parasitics. Most of those are parasitic inductance, but there's capacitance too. And so you can see if we look at this loop, through the switches, when we turn on an upper switch, we end up with this loop that connects through the capacitance of the lower MOSFET. And so in this case, what that noise is being generated by is the CdVdt of the capacitance of the logic gate's lower MOSFET. And so just the devices themselves are capable of creating relatively large amounts of noise. And it's also resonant because there are all of these little resonant parasitics in bond wires and pins and capacitor equivalent series inductance. And so this tells us that there's actually three kinds of noise that are generated in the power rail. There's CdVdt, which is actually the instantaneous noise. That's the one that created the 1.5 volt spike. There's average noise, and that's created by the repetition, and that's CVF. And then there's the resonant current, and the resonant current is V divided by Z0, where Z0 is square root L over C, and that tells us we end up with a resonant current that's V times square root of C over L. That's where the ringing is. Our logic example was a 300 picosecond gate, which is 5 volts and 300 picoseconds, and so we see this CdVdt, where that's 5 volts divided by 300 picoseconds multiplied by the capacitance of the lower MOSFET. Well, that works for VRMs also. When we look at where VRM noise comes from, it's exactly the same thing. And if you want to see where it is that that ringing on the leading edge comes from, well, you can draw that circuit again, and you'll see that there's a bunch of parasitic inductances, and you can see there's also parasitic capacitances. There are actually three of them that contribute to that ring. One is the capacitance of the lower MOSFET, or freewheeling diode. One is the capacitance of the power plane, and another one is the capacitance of the output filter inductor. And the parasitic inductance is the loop that goes through the input capacitor, through the upper MOSFET, returning through these capacitances and back through the input capacitor. In gallium nitride, these loops are very small. They tend to be very highly decoupled, and so the ringing frequency becomes very high, but also very high Q. And that high Q, that controls the amplitude of this ring. So what controls that ringing frequency and the ringing amplitude is the resonant frequency and the resonant characteristic impedance of that tank. And of course, that generates EMI also. And here we can see that, just looking at EMI, and I didn't even use a near field antenna. You can see I just put a telescopic antenna on my oscilloscope so I can measure the noise in somewhat far field to see what it is that comes out of this power supply. And sure enough, you can see there is that leading edge ringing frequency, and it shows up nice and clearly. So that's how that converts. And in that little switching power supply, there's also an inductor, and most of these inductors are tabulated, so we can buy them in almost any inductance, and this one is no different. I chose an inductor that's 320 nanohenries in this case, and one of the things that you might have noticed, or maybe not, is that they don't specify either this self-resonance or the parallel capacitance. They do say that it's good for a frequency range up to 2 megahertz, and our switching regulator is 1 megahertz, so I chose that inductor. We actually measured that inductance, and it's 300 nanohenries, right about where it's supposed to be. We can also see its resonant frequency here at 18.3 megahertz, and if you calculate the capacitance, that says that there's 250 picofarads of parallel capacitance. I also custom designed a toroid that would give us a much higher self-resonant frequency at 400 megahertz to see the effect of self-resonant frequency of the inductor and how it is that that impedance affects noise. And here's a comparison of those two inductors side by side. So the farad inductor that has 200 and some odd picohenries of capacitance, you can see this ringing that shows up in the output ripple, and also this really large spike. And so these, of course, are generating lots of EMI. If I take that same inductance, but put it into a custom toroid, you can see the custom toroid here in the picture. Notice those spikes are gone. And so that says that one of the big paths for EMI and output noise is the capacitance of the output inductor. And so for that reason, we need to measure all of these devices so that we can see it. Some of these parasitics get really small, and how is it that we can measure these parasitics? Well, one easy way when they get really small is to measure them using time domain reflectometry. Time domain reflectometers get to relatively high frequencies at relatively low cost. And so at about 10 gigahertz, it's pretty easy for us to measure femtofarads and picohenries. And so one way that we can measure those parasitics is just to put a TDR response where the switches are and measure that response. It generates these pulses. The pulses are either positive or negative in polarity. One polarity is a capacitor, the other polarity is an inductor. And if we integrate the waveform for each one of these responses, we can get inductance or capacitance. In this case, I'm measuring 150 femtofarad cap and 150 picohenry inductor. You can see here are the two integration equations. One of the interesting things about that is that the integration doesn't really depend on the TDR bandwidth all that much. If we reduce the bandwidth, like we did here in this blue trace, we end up with a wider pulse, but about the same integration. And so for measuring gigahertz, femtohenries, femtofarads, and picohenries, the TDR is a good way to do that. How do we stay out of trouble? Choose components really wisely and measure them. One of the rules that I have for our own designs is that we never use a component we didn't measure. The Bodhi 100 supports 7 different impedance measurement options so that we can measure anywhere from microohms to megohms. You can see this example here from my ultra-low impedance class, measuring 20 microohms with a Bodhi 100. It also supports incredible dynamic range. You can see we have 160 dB dynamic range measurement here, measuring a COG capacitor. But we will not use a capacitor that we have not measured. We won't use a component that we have not measured. So that's probably the best thing you can do to stay out of trouble, is measure the impedance of your components, measure the impedance of your circuits. The key takeaway, if there is one, is that SI, PI, PE, and EMI don't really have separate electrons. There isn't some gatekeeper at a checkpoint that says, all right, let me see your paper. So you a SI or a PI. All right, you go in the left lane, you go in the right lane. It doesn't work like that. All the electrons are the same. We give them names like SI, PI, and PE to make it easy for ourselves, not to make it easy for the electrons. The electrons know exactly what they're doing and where they're going. Our job is to try to figure it out, but they already know. I don't expect you to take my word for it. Well, I do. But in case you're not convinced that impedance is really the common denominator, of giving you some additional links here that you might find interesting, and it'll tell us how it is that impedance carries over for all of these 5 topics and how it is they interrelate. I want to thank you all for attending, and I want to thank OMICRON Lab in particular for making this symposium and for inviting me to speak at it. There are a couple of links that you might find interesting here if you're interested in more information. And of course, I'm always happy to hear from you guys. If you have questions, I'm happy to listen to them. You can email me at steve@picotest.com directly if you like. I'm always happy to get questions.